Ever wonder how robots navigate mazes without a map? It's not just about moving forward. It's about learning, adapting, and making smart choices in real time. Today, we're diving into hierarchical DDPG, a revolutionary approach that teaches robots to conquer unknown environments with precision. Let's unpack how this system works, why it's a game changer, and what it means for the future of AI. Here's the problem. Robots in mazes have no prior knowledge of the path. They can't just look up a map. They must explore, avoid obstacles, and learn from sparse rewards. Think of it like solving a puzzle with only a final gold star as feedback. Traditional algorithms like standard DDPG struggle because they can't balance exploration, trying new paths with learning, refining strategies. They either loop endlessly or take forever to find the exit. But what if we gave the robot a two-tiered brain? That's where hierarchical DDPG shines. Imagine a team, one person planning the big picture, another handling the details. The high-level policy acts like a GPS, setting intermediate goals, like waypoints, to guide the robot toward the exit. Meanwhile, the low-level policy is the driver, making real-time decisions based on sensor data, like adjusting speed or turning. Together, they split the brain power, making the robot smarter and faster. Here's the magic. The high-level policy uses an advanced DDPG variant to map out a rough path, while the low-level policy fine-tunes movements. But there's a twist. Traditional systems falter when the robot's skills evolve over time, like using an old map for a new city. To fix this, researchers added off-policy corrections, updating old experiences to align with the robot's current capabilities. They also introduced adaptive noise, a controlled randomness that keeps the robot curious, exploring new paths without losing focus. And let's talk about feedback. Traditional algorithms punish every tiny mistake, which slows learning. This system reshapes rewards to celebrate progress, like a teacher praising a student for improving, not just the final grade. If the robot avoids a wall or gets closer to the exit, it gets a boost. This keeps it motivated and prevents it from getting stuck in dead ends. But how does it process all this? The robot has a two-part brain, an actor and a critic. The actor is the decision-maker, choosing actions like turning left or accelerating. The critic evaluates those actions, assigning rewards based on success. In hierarchical DDPG, this duo works in tandem. The high-level actor sets subgoals, while the low-level actor executes precise movements. The critics, meanwhile, refine strategies by balancing long-term goals, like reaching the exit, with short-term gains, like avoiding collisions. Let's get specific. The high-level policy uses a reward-shaping technique, where each subgoal earns plus 100 points. This acts as a progress bar, keeping the robot motivated. Meanwhile, the low-level policy operates on dense rewards. If the robot gets within 13 cm of a wall, it incurs a minus 500 penalty, a danger alert. But it also gets a tiny boost for moving closer to its current subgoal, ensuring it stays on track without getting stuck in frustration. The results? Robots using hierarchical DDPG navigate mazes 30% faster than traditional methods, with 50% fewer collisions. This isn't just about mazes. It's about teaching AI to handle complex, real-world tasks like autonomous driving or disaster response. By breaking problems into manageable layers, we're creating systems that learn smarter, not just harder. So what's next? As researchers refine these techniques, we're one step closer to machines that don't just follow rules, they understand them. Whether you're a student, a developer, or just curious, this is the future of AI. Stay tuned, and let's keep pushing the boundaries of what robots can do.